Hi, I'm Nick Latrelet, and today I'm going to be talking about verifying the quantized nature of electronic energy levels through a series of experiments. It's called a blast from the past. The reason this presentation is called a blast from the past is because we did a series of 3 experiments, each one with a different significance for ultimately uncovering the quantized nature of electron energy levels. The first and earliest experiment was Louis Fizeau's. So we modernized his experiment to determine the speed of light. The second was investigating blackbody emitters and solving the UV catastrophe using approximations created by Wilhelm Wien and Max Planck. And then the third experiment was using line emission spectroscopy to actually quantify the transitions for hydrogen and deuterium. So our first experiment that we did was kind of a modernized version of Fizeau's experiment for the determination of the speed of light. Ours involved a laser which was directed at a pick-off window, which allows some light to pass through, some to be reflected back towards a detector. The light that passed through was directed towards a mirror, which reflects the light back through a focusing lens and into a final detector. The distance that the light traveled was recorded, and both detectors were hooked up to an oscilloscope, which allowed us to record the time difference between the moment the light hits the initial detector and the moment it hits the final detector. And then this experiment was repeated 5 different times at varying distances from the beam to the mirror. If you look in the top right-hand side of the screen, you'll see an example of an oscilloscope image for trial 3. You'll see an outgoing signal and an incoming signal, where the distance between these peaks is representative of the time it took for the light to travel along its path. For run 3, it was 67 nanoseconds. Below, you'll see a table with all 5 trials with experimental data being distance and time measurements. And then the third column will be speed of light calculated values using the equation to the left. All 5 values were averaged and was our reported value for the speed of light. Understanding the speed of light was very important for the quantization of energy, because you can't understand the energy of photons before you can actually understand the speed of them. So this was a very important step towards quantizing energy levels. Our second experiment was a study of blackbody emitters. A blackbody is an object that can both absorb and emit all wavelengths of light. This makes it an interesting topic to explore as it relates to energy. In this experiment, we explored 2 equations that describe blackbodies. From classical physics, we have Wien's equation, which uses Wien's proportionality constant, B, to relate the temperature of the blackbody to the wavelength of maximum intensity. This approximation works well in the visible spectrum, but at very low wavelengths in the UV region, the temperature approaches infinity, which is not actually what happens. This problem was dubbed the ultraviolet catastrophe. The second equation that was used to approximate blackbodies was Planck's equation from quantum theory. In this equation, Planck proposes that energy is not continuous, but has a discrete values. This concept is called quantization of energy. Planck's constant was developed to relate the frequency of a proton to its energy. This demands that all energy levels must be a factor of Planck's constant. This theory of quantization was first confirmed because Planck's equation for a blackbody actually solved the ultraviolet catastrophe. So this was a massive step in understanding the quantization of energy and the first hint at quantum theory. Before I could compare Planck's and Wien's equations, I had to obtain emission spectra from 5 different light sources. I used the ocean optics spectrometer with an optical cable, which was pointed at each bulb independently and recorded a spectra that looked like this. Before going to this experiment, I believed that the incandescent bulb would behave the most like a blackbody due to the filament not emitting a specific wavelength of light. It's just emitting light because it's reaching a high temperature, much like a blackbody does. Here we have the results of the blackbody experiment. In the table, you can see the experimental lambda max, which is the wavelength at which the highest intensity light was recorded. You can also see the temperature at which the Planck equation best matched the experimental curve, and you can also see the temperature calculated with the Wien equation. We confirmed that the Wien equation is a decent approximation in the visible spectrum, We can also see that as Planck's approximation approaches the UV region, it is decreasing, which confirms that his approximation did in fact solve the UV catastrophe. The first hypothesis was correct. The 75-watt incandescent bulb best matched Planck's approximation, which you can see below. Most of the other curves only had one point of intersection with the Planck approximation, where you can see here, like most of the peak is intersecting with the approximation from Planck's equation. The final experiment conducted was the line spectrum emission of hydrogen and deuterium. This experiment sought to confirm Planck's initial theory of energy level quantization. The experiment utilized Rydberg's equation to predict the wavelengths of light emitted due to the transition from upper energy levels to lower energy levels. In this equation, lambda represents the wavelength of emission, RH is the Rydberg constant of hydrogen, and N1 and N2 represent the quantum numbers of the transition. Rydberg's constant can be calculated with this equation here, where mu is the reduced mass of hydrogen's nucleus, E is the elementary charge, and epsilon naught is the vacuum permittivity. These are the theoretical values for the transitions of hydrogen and deuterium, calculated with all the equations mentioned before. This is an image of the experimental setup. First, we have a gas tube containing hydrogen and deuterium, and when current is added, the electrons of both gases become excited and begin to emit photons. Some of the photons hit this lens, which focuses the light into the monochromator. The monochromator slowly measures the intensity of light across about 1,000 angstroms, detecting specific peaks associated with energy level transitions. I expected to see more intense peaks as the quantum number of the upper energy level decreased. This is due to the lower energy gap, allowing more electrons to readily make this transition. These are the results of the line spectrum emission experiment. In the first graph, you can see that 5 peaks were identified by comparing to theoretical wavelength values that were previously calculated. Below, you can see the 4-to-2 transition peak, where there are 2 distinct peaks, one for deuterium and one for hydrogen. Off to the left, you have the table of experimental data, where we have wavelength values associated with each peak, one for hydrogen, one for deuterium. Using the equation below, we were able to convert from wavelength to energy values. This is where our experimentally determined speed of light value was used, that was determined in the first experiment. It demonstrates that it's very important for Fizeau to determine the speed of light and for Planck to determine Planck's constant in order to actually quantify these energy values. From the experimental data, I was able to plot 1 over the wavelength versus 1 over the principal quantum number for each transition. This was done for hydrogen and for deuterium. I created a regression curve for each set of data where the slope of the curve corresponds to the Rydberg constant determined experimentally. The theoretical values of the Rydberg constant when compared to our experimental data has a very small percent difference, demonstrating that line emission spectroscopy is a very powerful tool for understanding the quantization of energy. The experimentally determined Rydberg constants were then used to determine the mass of deuterium. An approximation was made that the mass of deuterium can be considered twice the mass of hydrogen. That is what you see in the second equation. When comparing the experimental and theoretical masses of deuterium, we see another small percent difference. Additionally, the Rydberg constants were used to determine the ionization energy of hydrogen and deuterium, and were compared to theoretical values derived from Bohr's model for ionization energy. We see again a very small percent difference. This indicates that the Rydberg and constants that we determined are very powerful tools for determining other constants relating to deuterium and hydrogen. The 3 smaller portions for this overarching experiment are all interrelated. Discovering the speed of light was very important as a first step towards quantization. It used classical physics, but it did lay the foundation for understanding quantum physics later down the line. There was also only a very small difference between Fizeau and my results, his being 3.15 times 10 to the 8th, and mine being 3.12 times 10 to the 8th. This is very surprising considering I had the use of an oscilloscope. For the blackbody radiation, I determined that Wien's classical approach had in fact failed, but it was a very important stepping stone for Planck to eventually make the theory of quantization. For the line spectrum, I determined that Rydberg's equation is extremely accurate when comparing theoretical to experimentally determined transition peaks. His equation demonstrates a full understanding of quantization. Also determined that quantifying energy can lead to other useful calculations such as mass and ionization energy. These are the references that I used for this presentation. I'd also like to just take a moment to thank Dr. Wagner and Ben and Elva for all their work they did. Thank you.